The experimental discovery of diffraction of electrons by crystals by Davison and Germer established the wave nature of electrons. Here is the similar setup to the experiment conducted by Davison and Germer. The setup is placed in an evacuated chamber. It consists of an electron gun G, a nickel target, and an electron detector that is capable of moving on a circular scale. The electron detector is connected to a sensitive galvanometer used to measure current. The electron gun G is used to produce a beam of electrons. The electron gun constitutes a tungsten filament F coated with barium oxide and can be heated with a low voltage power supply. Electrons are emitted by the filament, and these are accelerated at a desired velocity by applying a suitable voltage from a high voltage power supply. The electrons thus emitted are passed through a cylinder with a pinhole along its axis, producing a fine collimated beam. This collimated beam is directed to fall on the surface of the nickel crystal. The electrons are scattered in various directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector or the movable collector. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering. Theta, which is the angle between the incident and the scattered electron beams. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity I of the scattered electrons at an accelerating voltage of 54 volt and at a scattering angle theta equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From electron diffraction measurements, the wavelength of matter waves was found to be 0.165 nanometers. We know that the de Broglie wavelength of an electron is denoted by lambda is equal to h by p, where h is Planck's constant and p is the momentum of the electron. If the electron is accelerated from rest through a potential difference of v volt, then, substituting the values of mass of the electron, charge on the electron and Planck's constant, the expression for wavelength is obtained as 1.227 by square root of v nanometer. In this experiment for diffraction of electrons, the peak value of intensity was observed at 54 volt. On substituting this value in the equation and simplifying, we get the associated wavelength equal to 0.167 nanometer. This theoretical value is in agreement with the experimentally obtained value of de Broglie's wavelength for electrons. The Davison-Germer experiment thus confirms the wave nature of electrons and the validity of de Broglie relation. The de Broglie hypothesis has been the cornerstone of many advancements and applications in recent times. In 1989, the wave nature of a beam of electrons was experimentally demonstrated in a double-slit experiment, similar to that used for the wave nature of light. In 1994, interference fringes were obtained with beams of iodine molecules, which are about 1 million times more massive than electrons. The de Broglie hypothesis has been basic to the development of quantum mechanics. The de Broglie hypothesis also led to the field of electron optics. The wave properties of electrons have been utilized in the design of the electron microscope that provides higher resolution compared to normal microscopes.